Before I begin, there has been a bit of a backlash against my impromptu lecture, should we do what in the lab test. Um, Apparently demonstrators have been saying something and yada yada yada. Right. I'm still going to give the advantage to those who attend the lectures and encourage people to come next week for future random advantages. However, what I decided to do is the lab test, I'll make it so that you can do it with the real-time method, or you can create a similar example that runs on the FPGA using interrupts, if you prefer, or so you can choose which method you prefer. But I would say that if you were to do it the real-time way, it will probably be easier, so it's in your favor to do it with the real-time way. Okay. So what is it you're doing is you'll find out next week. You can use all previous code. Yeah, I'm fine with using, like I said before, you can use Google, you can use all previous code. I actually encourage you to do that because that's what I think you should do when you program. This is just my opinion and I'm allowing you to do that. Is there any other questions before we move on? It's 2.5 hours so that we have time to mark everyone off. But hopefully people finish beforehand. So there'll be a marking scheme, so you can see how far along you are, and with the demonstrators as well. I think, frankly, you could get it marked as you go, but I would just get it marked at the end, personally, because it would save you time calling demonstrators. On the day in the lab, and it will be different between every lab session. So you can't cheat. You have to delete your code once you finish the lab, so you can't pass it on to other people. Yes. So you have to. I'll send a Moodle announcement on this. You do have to attend your designated lab session for this, because at full capacity we have, I think, 176, obviously. And our lab is basically, they're packed to capacity. If you wanted to, you could probably come in on a Monday. That's the only thing I'll say. Monday morning at 9 o'clock. That would be your potential alternate option. But otherwise, attend your lab session and we'll check. And if you are not in the right lab session and there's no spare computers, then we'll have to kick you out and you'll get 0. That's just how it has to be. If there's any special reasons why you can't make it, contact me beforehand and we'll see if we can arrange something. Anything else? Right. To the lectures. We're carrying on with looking at compilation, and we got to the point of talking about data structures and how do they look like when we create them in actual software. So first up, you should be aware different data structures use different layouts, which should be obvious. We have some data structures which we can compute at compile time, others must be computed at runtime. What are these runtime ones? Anyone? No dynamic data structures? Anything? So how does it increase the size? So this, exactly. So basically anything with malloc or the equivalent, calloc or whatever you use in Java, etc. So yeah, any fixed data structures Now, exercise is recommended for you to do, and it is recommended. I don't know if anyone will actually do this, but it may help you in the exam to compile various different data structures, see what they actually look like in Neos code. It won't actually take you long to do, and you can have a quick flick through, just covering what certain data structures look like. So an array, you should be aware of the idea. You have an array which have an index or which points to the first location in memory for this array, and then you offset each memory location by so you dereference the memory location of a plus 1 to get value a, and they're stored in consecutive chunks of memory, consecutive bytes, all the way down. What happens with a 2D array is that typically you don't have 2D memory structures in terms of your software. You just view this as one very long data structure. So you have to basically pick a row major order or a column major order, and this will depend on your programming language, which they choose. Here we've shown a row major order where, so I have n rows, m columns. How do you find out the offset? Well, if you go I times m, so first row 0 times m, you work your way across. Second row 1 times n, you work your way across. And that corresponds to coding that straight down the memory. It's just a simple translation, and you'll probably have written something like this over the course of your various programming that you have to do in this degree. Fields with structures can have which have static offset. So you can work out how much memory is needed at compile time. So for a long, here you might need 4 bytes. For a character, you need 1 byte. So you just have your structure. You have a pointer to the structure, which points to the start of this area of memory. You have 4 bytes allocated to store the long, and 1 byte allocated to store the field. And to access the field directly, because you know the offset, you can just it directly access the character by knowing the number of bytes offset. Okay, unions, you've probably never used these. These are a bit rare, but you would use them when you really see memory as a scarce resource and want to share memory. And so in this case, we have the same long and character sharing the same memory space. Okay, so how do we know which one's in my memory? Well, this is actually up to the user to ensure that he doesn't try and write 2 things at once and jumble things up. But you always assume that either the character, the field to the character, or the long is stored in the memory, and it's always pointed at the start of the pointer. So you don't have this fixed offset thing, and we can only store 1 at a time. Note that you pick 4 bytes because 4 bytes is bigger than 1 byte. You need to be able to store the bigger of the 2. So that's rather straightforward. What's more interesting to me, at least, is this idea of optimization. And you're trading off various characteristics of code size, execution time, or resources as in terms of memory or registers. It's how do you play with what you have available to get your fastest design in general. Now, you might have a longer code size, but you have less branching and looping, so it's faster. You get these sort of trade-offs. Right, so let's have a look at a few. So there's straightforward ones which are speed-ups for free, right? If anyone ever wrote 8+1, you would never actually implement that in your code. You would just pre-compute it that 8+1 is 9, and whenever you use 8+1, you use 9 instead. Similarly, You can have algebraic manipulations. You know that in integer arithmetic, that a times b plus a times c is equivalent to a times b plus c, simple algebraic manipulation. For those who are interested, this is a total aside, but this is not true in floating point arithmetic, which is what you use all the time. So yeah, if anyone wants to speak about this with me, come to fourth year courses and we'll have some fun. Strength reduction, again, very common in hardware, but it also exists in software because you often have the ability to do a shift at the same time with some other operation, so you can do the shift for free. So instead of doing a multiplication, which is costly, if you've got any power of 2, you just do a left shift or a right shift. And probably more important for division, because division, quite often you don't have dedicated division circuits, you'll have some division algorithm. So avoiding an algorithm with a single command saves a lot of execution time. Dead code elimination. So you could write some software and you've written a heap of program and then you've edited and changed it over time. And you can actually get parts of code which you're never actually going to reach because of conflicting conditions. Now this is really good to eliminate because it's a total performance gain, right? You're just saving memory which could be allocated. You're saving a lot of code size, which just wastes space if you're constrained. The problem is this is an incredibly difficult thing to do. This is always a constant active area of research, and if you're a compiler guy, this is what you would work on to some degree. And also very much in academia in computer science. Okay, procedural inlining. If you have a function, a simple function, a plus b minus c, which you call throughout your code, you could, instead of calling the function just as a compiler, replace this foo with the function itself. So that is, again, a trivial optimization. The trade-off here is that if you call foo 500 times, then you repeat you add this extra code for foo 500 times. You actually increase your code size substantially. Who can tell me why it goes faster? Yeah, so it's not interrupt, but you basically have to pass all of your data, get it all ready to pass into the function to be into the correct form that the function can run. And we'll talk a bit more about how you link within procedures to show this in more detail later on. Okay, loop unrolling. This is a simple one. So if I've got a loop, here I have a for loop, I go for I is 0, I is less than 4, I plus plus. I compute some multiplication between two vectors and store the result of this multiplication. Equivalently, I can unroll this into two operations. All I've done is I've changed the offset here, and so that would allow the second one. So writing the extra line of code, this allows me to speed it up. Is this clear to everyone why it can speed up? No? Maybe? Some? Right. I've decided I'd write this out. So, if I wanted to write in an assembler a for loop, how do I do this? So, initially, I set a register to have the value of 0. So I move into register 2, 0, which register 2 is going to store the value of I. So I is initialized to 0. Then I do a comparison. Comparison if it's R2 is greater than equal to 0. sorry, if R2 is greater than or equal to 4, then I'm going to branch to the end. Otherwise, I continue on my code. Quick question, why do I do this branch if not equal? You can imagine I'm going to have some loop and I'm going to come back to this code at the bottom here. So I could, instead of saying compare R2 if it's greater than 4, I could say branch if it's equal and it's less than 4. Yeah, this is what I was saying before, is generally you care for the, I'm going to go down this code first rather than branching, which is the worst case. Okay, what do I do next? I have to work out what BI and CI are. So say I load into R3 address B, and then I add R3, R3, R2. What am I doing there, anybody? Yeah, yeah, I'm computing BI, not just, so B is the base address. As I go down this loop, I need to offset B. So add R2, which is I. So now R3 has BI. I repeat a similar thing, R3 with R4 with address C, add R4, R4, R2. So now R4 has CI, and then what do? I do my multiplication. I multiply R3 by R4. That holds what I want to be AI. So now I need to work out where to store it. So again, load, say R5, address C, add R5, R2, work out the location of AI, and then I store into the location pointed by AI, I store my value for AI. Okay, so that's my simple version. Anything else missing? People to think about assembler, think about the code they're getting. There's some obvious flaw in this code. Yeah, increment R2. R2, R2, add 1. Add immediate. Now technically, if you're a bit careful, you should maybe say that I might want to compare to 16 and 4 at a time, because actually you have to address byte offsets by 4. That's just being picky. Now, first up, who thinks that's good code? Sweet. Yes. This is probably what you get if you compile it straight on the NEOS, but this is not optimized. Who can tell me, have a think what I'm doing that not too well here? Yeah, I've got 3 loads of address. Really, you should pull this out top if you were doing an optimization. Load them once, store them in registers, and work it off that way. Okay, so but what I wanted to show is, why do you benefit from loop unrolling? Well, the advantage is, if you loop unroll, with this code here, what do I gain? So what I would have is basically this same code repeated again before the branch statement. but with an offset of 4. Do I gain anything from that? Speed. How?
Because it doesn't have many branches.
Yeah, so I've saved one branch operation per loop. So I've divided, if I have, here I have four iterations, but if I had n instead of 4, then, so that was n, then I would save n branches. And branches are actually quite a costly operation because you're flushing your pipeline whenever you branch on the CPU. So it's actually quite costly. There's actually another cost is if you wrote this better, you know, on a NEOS you actually have instructions which are like load R, R4, R5 with an offset of 4. Why would that be of any benefit? Say this was the equivalent of what I have here, then by having this fixed offset of 4 and a fixed offset of 0, I only need to compute the address once. So I can compute the address once. I wouldn't have to repeat those 2 lines. I can shrink them down into, instead of 4 lines, I would have 3, and so on and so forth. So there's various optimizations you get from this when you're talking more and more loop unrolling. The payoff, obviously, is you get longer code. So it's not always ideal. If you have a limited amount of memory space, your code is eating into your memory space. You might not actually desire that. Okay. For the record, who thinks in this example unrolling by 4 is better? Hands up. Who thinks it's worse? 1 person thinks it's worse. 2 people thinks it's worse. Right. We have a very special case that if you were to unroll by 4, this would be basically an always better. So there's 2 people I'm afraid are wrong. The reason is, of course, if you unrolled by 4, you no longer need, right? You save all branching, looping operations, and your code would actually be smaller. So there are various trade-offs there. It's worth considering in detail. And when you consider these optimizations, you do have to kind of think in assembly. Speaking of assembly and compilation, I mean, you might think I'm mad here, going on in such effort about gaining a couple of lines of code. The advantage is that this couple of lines of code is done automatically. So from a user perspective, it's completely free, right? They just type in optimize when they compile, and your code runs faster. And that's why a huge amount of effort, you know, it's continuous ongoing at your MIPS, your ARMs of this world, putting massive effort into just making their compiler just a tiny bit better, because a tiny bit means a lot over the amount of ARM code that you use when you consider that your iPhone has like 4 ARM chips inside it. Okay, and this is an example of at the same time your NEOS, your basic compiler can often be inefficient. This is an example of a switch statement with your various code. So, right, I have my C code in kind of red and various bits to look at in highlighted in cyan and yellow. Right, so what's a bit odd? Let's look at this code here. I store R2 into frame pointer minus 12, which R2 has the value of I. So there's this diagram here. R2 is stored into frame pointer minus 12. And then I load R2 into frame pointer minus 12. Who thinks this is a good idea? Can anyone explain why I would ever store it and then load it straight away? Sort of, what it's thinking of is that I'm going to have to reuse I multiple times and I might change it. So let's store the value. But there's no real, and then as I come around this loop, then I might need to reload this value further on. But there's obviously room for some optimization there if you use the spare register, which you probably have further down the code, which it hasn't gone to optimize. Similarly, what is wrong with these 2 bits in yellow? So here I'm comparing registers and I'm branching if greater than equal to, and then further down I'm branching if equal to 2. Can anyone see any problem there? Yeah, this one will never happen. So what should I do with this code? Get rid of it? Any other votes? No, 204. It's true. So it's fine. It's a good idea. So it's greater than equal to 2, so I branch somewhere here, and then I compare if it's greater than if it's equal to 2, and then I do something else. Well, I haven't. Well, look. Well, the point is, you might want to take one path if it's greater than equal to 2, and a second path if it's equal to 2. But you should check if it's equal to 2 first, and branch once, rather than branch twice for the greater than or equal to 2. So that, again, is a compiler optimization. This is obviously how the person's written the code, and the compiler's just done a single pass and translated this into assembly. And this is why you have multiple pass compilers. Now, the Neos, what's the base compiler, does these kind of inefficient things generally. So this is why it's kind of looking a bit into detail to sort of understand it. Okay, an interesting optimization is this area of caching. Okay, so how does cache work? Cache is a local bit of memory on your chip. So you think of your computer chip. Your modern processor has the immediate processor with a couple of registers around it. Then it has level 1 cache, which is memory that's close to these registers, level 2 cache, which is a bit more memory, which is a bit further away, level 3, which is a bit further away still, but a lot more memory. And you build up in this hierarchy all the way down to somewhere your off-chip memory. And the idea is that you want to load similar data into the cache so that every time you want to access memory, you don't have to go all the way down the chain. You preload a big chunk of it at once, and then hopefully you can reuse that chunk. And it's based on the idea of spatial locality. Now, spatial locality makes sense because you write a lot of code like this. You have a lot of loops, and loops increment in small little bits. And you can see that a lot of this memory is going to be close together. So you could preload some data and then access it from the cache quickly. Okay, the question is, how do you use the cache efficiently? So here I've got a cache which can hold 16 items. So this whole block here is my cache. And whenever I load the cache, I load one entry and the next 4 items in a row. So if I have my 8 by 8, which is A, so this is 8 by 8, what I do is when I do my first operation, I look for A00. Yeah? So A00 is here. Is it in the cache? No, it's not initially. So I grab A00, but I don't only grab that. I also grab A01, A02, A03 at the same time from main memory and store this in my cache. Okay? So then I carry on in my loop iteration, and next I look for A10. So now I say is A10 in my cache, and my cache currently holds these elements here. So is A10 in that set of 4 elements? No. So I have to grab the next 4, and the next 4. And you can see with this kind of loop structure, I'm actually never going to get the hits. And then eventually what's going to happen is as I get to here, my 5th entry, I've already completely filled my cache. It'll look like is here. When I look for A50, A50 does not exist in the cache, and there's no more room in the cache. So not only do I not get a hit, I have to spend energy replacing what's there. So, though really, a replacement and a miss are about equivalent in cost. But the problem is, okay, so I finished my first row, then I next want to do so after I've got A70, the next element I should access is A01, just by looking at the loop code. Okay, so I'm looking for A01, and this is the state of my cache. Is A01 there? No, it's not, so then I would load A10 here, sorry, A01, and then this would be A02, A03, A04. So you can see I've not had any hits. I'm reloading the cache, and if my cache was 1 row bigger, then I would have had a hit because I previously had it in there, but I've had to replace it. So I've lost this free performance gain. So who can suggest a solution to this problem? Preload? You can't preload because it is kind of preloading, right? It's preloading with the cache, but it's getting the wrong elements preloaded. There's a swap I and j. Someone said swap I and j. What happens if we swap I and j? It's very simple. So again, first I access A00. What do I access next? I access A01. So A00, it brings in, fills up this first cache line. So A00, bring in the first element, fills in this cache line, and then A01 is ready. So then I can do A01, then I can do A02, A03. Now, when I get to the next 4, 5, 6, I'm going to have 1 miss and then 3 hits. And that's going to continue on. So I have 1 miss, 3 hits, 1 miss, 3 hits. So in the case of 64 memory loads, I then only have 4 memory loads. And most of the time I'm just using my cache. Right, there is an alternate solution, which is a bit complicated, but anyway. So you can instead break up your array access so that I break up my 8 by 8 array into a 2 by 2 grid, and then I go across my individual 2 by 2 grids, obeying my original order. Would that work? Well, what you would have, you first load A00, you'd get 4 elements in here, then you'd have A10, and you'd load the next 4 elements. Basically, after 4 loads, you would get to my original state here. Right. Same 4, but then because I've broken up my structure, instead of carrying down, looking at A40, it instead looks at A01, which is already in the cache. So you have 4 misses, and then you have 12 hits. And then you do that for the next block, and the next block, and the next block. So you can work through that in your own time. Which one's better? Well, this loop tiling approach in this example, it's a lot more complicated for one. You can have a lot more branch operations. So it's not going, and you don't save any cache hits. You don't get any extra cache hits. So it's no better in this instance than just changing the loop order. If you got a more complex example with multiple arrays, then actually loop tiling for this reason can give you performance advantages. So that's just worth knowing. Last slide in this section, talking about interpreters and JIT compilers. This is just for your knowledge. An interpreter translates an execution and executes program statements as you go. So it's a lot less, you gain a lot less performance than you would with a compiler because there is no compilation. It just does the instructions as you go. The trade-off is it's typically a lot faster, a lot easier to use in terms of running, and you can actually stop the program at any point because it hasn't compiled it and changed the order of your program. So here it has Visual Basic as an example. You should all know a much more commonly used example. Your most common language probably? Python. Python is actually, yeah. I was actually thinking MATLAB. I'm guessing a lot of you use MATLAB. You have somewhere in the middle, you have JIT compilers just in time. So it compiles code as you need it. So somewhere in between the two. And this is what's used in Java. Okay, on to the next section, which is talking about assembly and linking. Right. Along to our map, we're looking at the assembly and linking phase. So I've also moved some extra code which was previously in the compilation phase about how you assemble procedures. Okay, so first up, assembly and linking is to do with multi-module programs where you have mapping relative addresses in different programs to absolute addresses, because obviously if you have multiple module programs, as you compile them temporarily to have a initial address, and then your linker then says, okay, the actual address of this function is this, and you put the two together and work out your code. And assemblers perform two main tasks, which you first go through pass of your code, and you write all your labels. You say, I have address A, address B, and I don't worry what that address is. And then you also build a table which says address B is actually this, address A is actually this, variable this A is actually 8. And then you pull these two things together and create code. Right. Going back a bit, linking within procedures, this is worth knowing about how you pass parameters into a function. And you can pass parameters either on the stack or using registers. Which is better, stack or registers to pass parameters? Doesn't care. Who thinks stack's better? Hands up. Who thinks registers are better? 50-50. No one cares. Stack will typically take more time to use because you have to load the stack because your data is currently on registers. So if it's already in registers and you can just pass it in registers, it can be faster. However, if you need the spare registers to use within the function, then you need to pass it on the stack. It's basically your trade-off. How does it look? Oof. This slide makes me have a heart attack. But hopefully, we're all good. Okay. So what happens when we call a function? So we're starting off in the program main, and we call a function example1, then we call a printf, and a second printf, where the second printf calls example2. Let's look at what's going on within the code. So first up, when you call a function, generally what you want to do is allocate some stack space where you can store your variables. This is the first thing. You have a stack pointer and you grab 24. So this is saying you have 4 bytes, so we're going to grab a stack space of 6 spaces, which is shown in this block here. So I have my old stack pointer at this point. I subtract 24 from it, so that's going down 1, 2, 3, 4, 5, 6. So the first thing I do is I change my stack pointer to this new address, and now I've got this is my working memory for this function. Okay, what do I use this working memory for? I first store the return address, because I'm going to have to eventually exit this function. I don't want to return to the higher function. Then I store the old frame pointer. Now the frame pointer allows you to look at all the locations of memory of your variables within a function. So basically, whenever we're addressing variables within this function, we're going to go for offsets from this frame pointer. So frame pointer minus 4 is Z. Frame pointer minus 8 is Y. Okay. So, however, what I also needed to, because I've gone to a lower function, I first store the old frame pointer and put the new frame pointer to be my offset. And I'm going to work from this offset. Okay. To run example 1, first I have to get all of my code ready to go in example 1. So, add R2 frame pointer minus 8. So, into R2 I'm going to put frame pointer minus 8. What is frame pointer minus 8? Frame pointer minus 8 is Y. So I'm storing, so I have the address of where I want Y to be stored into R2, and then I store R2 or Y. Similarly, I store Z, then I move